Hello, everyone. My name is Michael Lamb, and in this presentation, I'll be talking about the new GAMSELECT procedure for generalized additive model selection. This procedure is new in the 8.5 release of SAS Visual Statistics and SAS Via, and it was developed by my manager, Wei-Jia Kai, and myself. This talk will use a simulated data example to demonstrate the selection methods supported by Proc GAMSELECT, and it focuses on the following three questions. First, how does Proc GAMSELECT fit and select generalized additive models? Second, how does Proc GAMSELECT compare to other related procedures in SAS software? And finally, and maybe most importantly, what are the benefits of using Proc GAMSELECT? So what type of problems might it be able to help you solve in your day-to-day work? To begin, though, I want to provide a brief high-level overview of generalized additive models. Generalized additive models, or GAMs, can be used to build flexible and interpretable models for a variety of different response types. A typical setup will assume independent observations of a response from a distribution in the exponential family. So that could be using a normal distribution to model continuous response data, a Bernoulli distribution to model binary response data, or a Poisson distribution for count data. Like a generalized linear model, or GLM, a GAM models the mean of the response by using a link function G and an additive model comprised of component functions f1 to fp, each a function of some predictors x. As the name implies, a generalized linear model further assumes that each of the component functions are going to be linear. GAMs extend GLMs by allowing the component functions to be an arbitrary smooth function, typically estimated by using splines, which allows for increased flexibility in terms of how you can model that mean of the response when there might be unknown nonlinear dependencies. To illustrate this point, here is a small example where I've simulated 500 observations from a normal distribution where the mean depends on one predictor x through a sine function. The figure on the left shows the traditional GLM fit using a normal distribution in the identity link, and the figure on the right shows the corresponding GAM fit with the same distribution and link function, and it's clearly doing a better job of capturing that nonlinear dependence. SAS Visual Statistics and SAS Via currently provides a number of tools designed for building GLMs and GAMs. In particular, some of you might be familiar with the GenSelect and GAMMod procedures. To understand how the new GAMSELECT procedure fits into this picture, you can consider three features of a procedure. First, if it allows you to control the sparsity of the model fit, so does the procedure support model selection? Second, if you can control the smoothness of nonlinear spline terms in the model. And third, if the methods that the procedure implements to fit a model are designed specifically for GAMs. The GenSelect procedure is designed primarily to support the selection of GLMs. While you can use regression splines in Proc GenSelect to model nonlinear dependencies, it does not support tools for easily controlling the smoothness of these spline terms. Moreover, because the procedure is designed primarily for GLMs, there are likely to be performance implications when you try using it to fit and select models with a large number of spline terms. The GAMMod procedure is designed to fit GAMs by using low-rank regression splines. It will allow you to control the smoothness of the model fit, and it is designed specifically for GAMs. However, it does not support model selection and does not provide tools for controlling the sparsity of the model. The GAMSELECT procedure supports methods for both fitting and selecting GAMs while controlling the smoothness of the model fit. It does so by using implementations of a boosting and shrinkage selection method designed specifically for GAMs. One point of comparison not on this slide is that the GAMSELECT procedure does not support inference on the fitted model, whereas Proc GAMMod does. Also, while there are procedures in SAS Stat software that are analogous to Proc GenSelect and Proc GAMMod, there is no procedure in SAS Stat software analogous to Proc GAMSELECT. So with that overview covered, let's begin by discussing the boosting selection method in Proc GAMSELECT. Proc GAMSELECT implements a component-wise version of a functional gradient descent or boosting algorithm. The boosting selection method in Proc GAMSELECT supports selection of parametric effects, so components that assume a linear model, univariate spline terms, and bivariate spline terms. At each iteration of the boosting algorithm, component-wise fits are obtained for each term, and one component is selected and used to update the model. Parametric effects, specified by using the param syntax, are fit at each iteration by using ordinary least squares, and the univariate and bivariate spline terms are specified by using the spline syntax and are estimated by using penalized B-splines. So it's those penalties on the B-splines that allow you to control the smoothness of the model. To illustrate the steps involved in the boosting algorithm, consider the following data with a response y and 4 continuous predictors v1 to v4. The algorithm begins with an initial model that by default is an intercept-only fit, shown here by the red line. The algorithm then repeats a second step until a stopping criterion is met. The second step begins by computing the derivative of the loss function given the current fit. For proc GAMSELECT, the loss function would depend on the negative log likelihood function, determined by the distribution and link function that you've specified. And evaluating that derivative gives the UI values plotted here based on that initial intercept-only fit. Next, for each of the individual terms, a model is fit to the UI values. In this example, that gives us the 4 component functions, gamma1 to gamma4, plotted here in red. Note that as shown here, the algorithm by default fits spline components at each iteration with a small degrees of freedom, so a more smooth fit. This is because the goal of the algorithm isn't to quickly converge to an optimal solution. Instead, we want to use the algorithm to efficiently generate a fine exploration of our model space, from which we then select our final model. Given the gamma1 to gamma4 functions, we now select for update the component with the smallest ASE with respect to the UI values, which in this case is the gamma4 function. So this effect is now updated in our model. Since this is the first iteration, it is now the only effect in the model at this point. And note that the model updates use a small step size, by default 0.1, and once again that's to try to support a fine exploration of the model space. The process of computing the derivatives and fitting the component functions and selecting a component for update would then be repeated until a maximum number of iterations or an early stopping criterion is met at iteration, say, m-end. At this point, there are m-end plus 1 possible models to choose from, with 1 model corresponding to the cumulative fit at each one of those boosting iterations. The final model is selected from this set, and here you can see the selected model and the partial residual plots for that model in our toy example after 500 boosting iterations. Let's now look at a larger example that demonstrates how you can use the boosting selection method in proc GAMSELECT. For this example, we'll consider a simulated data set with 10,000 observations. The data include 200 continuous predictors, v1 to v200, and the true model for the mean of the response y depends on only the first 4 predictors, v1 to v4. So in this example, there's going to be a very large number of noise terms. Here I've plotted the true form of the component functions f1 to f4. We have a sine function of the variable v1, a quadratic function of v2, a linear function of v3, and an exponential function of v4. And the error terms are being generated from a standard normal distribution. The syntax for specifying a model in proc GAMSELECT is consistent with other SAS procedures for fitting generalized additive models. Here I'm defining the spline prefix list macro function and using it to specify spline terms for the variables v1 to v200, all using the default spline construction in the model statement. When using proc GAMSELECT, both the model and selection statements are going to be required, and in the selection statement, I'm indicating the use of the boosting selection method. Looking at some of the output from these statements, the iteration summary table shows that 500 iterations were executed. That is the default number for the boosting selection method. That the selected model corresponds to the final boosting iteration, and that the selected model includes 8 effects, not counting the intercept. The selected effects table shows us the 8 selected spline terms, the iteration at which a term first entered the model, and how many iterations a term was selected for update. You can see that the 4 true effects were selected for the majority of the iterations, and that the 4 noise terms were selected a small number of times towards the end of the algorithm. This model yields a good fit with an ASE of about 1.04, and an oracle model should have an ASE of about 1 in this case. So this is a very good fit. One very nice property of GAMS is that the univariate and bivariate spline terms can easily be visualized, which allows you to better understand the contribution of each term towards the model fit. So GAMS provide you with a very flexible and interpretable class of models. These smoothing component plots were requested by using the plots equals option in the proc GAMSELECT statement. And here we see well-reconstructed curves for the variables v1 to v4. The plots for the spline terms constructed from the noise terms selected in the model show small contributions as indicated by the scale of the y-axis. One concern you might have when using the boosting selection method is that when run for a large number of iterations, you can end up overfitting the training data. 2 options you can use to attempt to prevent overfitting are to allow for early stopping of the selection process, or to change the selection criterion to be either cross-validation of the ASE or the ASE on a validation data partition. Here I'll refit the model by using cross-validation and early stopping based on a relative change in that selection criterion. With these options added, the selection process now terminates at the 300th boosting iteration and selects a model with only the 4 true effects. This model has comparable training data ASE and cross-validation of the ASE with values of about 1.08 and 1.1 respectively, so again, a pretty good fit. Looking at the smoothing component plots for the selected model, the curves for the variables v2 to v4 look pretty good, but the curve for the variable v1 shows a more linear fit in the tails, suggesting some possible over-regularization in this case. Over-regularization can be controlled by adjusting the degrees of freedom for the spline term that's fit at each iteration of the boosting algorithm, as increasing the degrees of freedom will decrease the penalty parameter used when constructing the penalized B-splines. When using the boosting selection method, you can use the df equals option in the spline construction to specify the degrees of freedom for a spline term. Here I refit the model one last time, now using only the 4 terms v1 to v4, with the spline v1 fit with 10 degrees of freedom at each iteration instead of the default 4. Doing so results in a very good model fit. And the smoothing component plots for this model show well-reconstructed curves for all 4 variables. Now, because most people, when they think of boosting, probably think of the type of boosting algorithm as implemented by the grad boost procedure in SAS Visual Data Mining and Machine Learning, I want to quickly comment on how the grad boost and GAMSELECT procedures compare in terms of their usage of boosting algorithms. And ultimately, this comparison is pretty straightforward. Proc GAMSELECT implements a component-wise boosting algorithm to build a generalized additive model. Because the parameter estimates for each of the components of that model are additive across the different boosting iterations, you end up with one generalized additive model at the end. Proc Grad Boost implements a tree-based boosting algorithm to build a tree ensemble. So in my outline of that boosting algorithm earlier, what would change is in step 2, now a tree is being fit at each iteration. And because those trees aren't additive in their estimated parameters across the iterations, you end up with a tree ensemble at the end as opposed to a single tree. For those who are interested in an example that further illustrates these differences, the paper that corresponds to this talk in the SAS Global Forum 2020 conference proceedings includes an analysis of the example data using Proc Grad Boost that for time I've omitted from this presentation. So to summarize the boosting selection method in Proc GAMSELECT, you can use it to build generalized additive models comprised of parametric effects, univariate, and bivariate spline terms. At each step in the algorithm, one effect is selected for update in the model, and that model can be based on the training data ASE, cross-validation of the ASE, or by using a validation data partition. So let's now move on to discuss the shrinkage selection method in ProcGAMSELECT. Because the shrinkage and boosting selection methods use very different algorithms, they're going to support different modeling options. The shrinkage selection method only performs selection for spline terms. All of the parametric effects that you specified in the param syntax are going to be included automatically in the model fit. The splines are modeled by using natural cubic splines instead of penalized B-splines, and the shrinkage selection method does not support bivariate spline terms. The shrinkage selection method performs penalized likelihood estimation by optimizing a function that involves up to 3 penalty terms. While I show here the full equation that is going to be optimized by this method, don't worry too much about the individual components, and let me just try to summarize some of the main portions. First, we have the negative log likelihood function, and then these 3 penalty terms with tuning parameters lambda 1 to lambda 3. The first penalty term with tuning parameter lambda 1 is like the group lasso penalty that can be used to induce sparseness. The second penalty with tuning parameter lambda 2 is the smoothness penalty on the second derivatives of the individual spline terms. And the final penalty with tuning parameter lambda 3 is like a penalty from ridge regression. You can either specify the values of these tuning parameters lambda 1 to lambda 3, or by default, ProcGAMSELECT will perform a grid search over their values and return the model with the best fit. So let's now see how you can use the shrinkage selection method for our simulated data example. Here I've once again used the spline prefix list macro function to specify a model with 200 spline terms. The shrinkage iteration summary table tells you the number of penalty parameter sets that were tried, in this case 200, the number of those tries for which the model fit converged, how many iterations were performed for the selected model, and the number of selected effects. In this example, there are 6 selected effects, now counting the intercept, and they include the 4 true spline terms plus 1 noise term. By default, 2 tables are produced to summarize the penalty information for the selected model. The regularization parameter summary table displays the information about the tuning parameters, lambda 1 to lambda 3, and the spline regularization table shows the penalty specific to the selected spline terms. These involve the lambda values, the spline-specific weights, phi and gamma, and the penalty function values. The smoothing component plots for this model show well-reconstructed curves for the variables v1 to v4 and a small contribution from the one selected noise term. For the shrinkage selection method, you can further refine the model fit by using a data adaptive approach to set the spline penalty weights, which would be similar to the adaptive lasso. Here we use that approach, refitting the model using the spline terms selected in the first model fit by using ProcGAMSELECT in the shrinkage selection method, now with spline smoothness and spline sparsity weights set based on 1 over the respective penalty function values from that first model fit. Doing so results in a model that now selects only the 4 true spline terms plus the intercept, and this model has a very good fit with an ASE of about 1.02. So to summarize the shrinkage selection method, you can use this method in ProcGAMSELECT to fit models comprised of parametric effects and univariate spline terms by using a penalized likelihood approach. Unlike the boosting selection method, selection is performed only for the spline terms, and the spline terms are modeled by using natural cubic splines. Models can be fit based on the fit for the training data or by using a validation data partition. So no cross-validation is supported when using the shrinkage selection method. And you can use those spline penalty weights to fit a model in a data adaptive way. So to summarize this talk in terms of those 3 opening questions, ProcGAMSELECT fits and selects generalized additive models by using the boosting and shrinkage selection methods. It provides tools that you can use to control both the sparsity of the model fit and the smoothness of the spline terms, a combination that is unique to this procedure in SAS software. and it implements selection algorithms that are tailored to generalized additive models. You can use ProcGAMSELECT to build models that are flexible, interpretable, and parsimonious, even in situations where there might be possibly unknown nonlinear dependencies. Thank you for watching, and for more information about the GAMSELECT procedure, you can see the corresponding paper in the SAS Global Forum 2020 conference proceedings. Thank you very much.